Hello.
Hi, hello. How are you?
Uh, just stressed out.
Yeah, I can imagine because the test's tomorrow, so that's a little bit stressful, right?
Yeah.
Okay. Um, I know today you're probably quite tired, and these tutorials are quite long. So if you want to take a break at some point, we can maybe take a break in an hour or so if you want.
All right.
Um, the last question we were kind of in the middle of this question with the elastic band.
Yeah.
Okay, and now I've got, I think, a better. Can you see on my screen? I have a board,
Yes.
the whiteboard. Okay, I think this one's a little bit better than the one built into Zoom because this one allows me to actually put the questions. So now I just have to find where is that. Okay, it's some of my wife's stuff. Okay, recent. Okay, so from here, now you can see the actual questions.
Uh, no, I can only see the board still.
Uh-oh, okay. Let me see.
Where do you save your questions?
These are on a computer. This is on the university computer.
Okay. When you share screen,
Yeah.
instead of just choosing one thing, just share your whole screen, I guess, because it's only focusing on that Google Chrome tab.
Oh, I see. Okay, so
Yeah, it's like a privacy kind of thing. If you choose just the Google Chrome tab, it won't show anything else on your computer.
okay, so one thing I'm trying to do. Okay, I have this. Let me see if this works. So you can see the whiteboard now,
Oh,
and
oh, yeah, I see it. I see it. That
now you can
that
see some
works.
questions too, right? Okay. So here's the questions I was talking about. So I drew out this elastic band thing when I was explaining this question. So, okay. We left off yesterday. We did the dimensional analysis for this. So we did, let's see, I can draw, let's see. Yeah, so we got for question A, it asked us to use dimensional analysis to get a formula for V1. We got V1 is proportional to square root of K over M times L, right?
Yeah.
And we started to do B, but we didn't quite finish because we had this Pythagorean theorem to get the length of the elastic band and all that, right?
Yeah.
So for B, we had conservation of energy. So we had half m v1 squared. That's the kinetic energy, and that kinetic energy, it's coming from elastic energy. So that's half kx squared.
All right.
And the x was the thing that was pretty hard to get because that x is basically how much has the elastic stretched. So this elastic has a spring constant of k, and so the amount of energy it has is half kx squared, where x is the amount that it's stretched away from the equilibrium.
Yeah.
We know the original length is 10L. That's what it says here. 10L.
Okay.
And so we want to find out, we know the original length of this elastic band, and we want to know what is the final length of the elastic band after it's been stretched. So that's where we have this 4 root 3L and this 3L and this 4L. And with that, we have to figure out. So it's going to be, we have, for example, let me change the color. So we have this right-angled triangle here.
All right.
That one, did you work this out?
Oh yeah, we did figure out the Pythagorean length.
Yeah, but it was a nasty formula. We had to simplify it and everything, right?
Oh yeah.
So you didn't. If you simplify everything, we should end up getting 16L. So do you want to go through that, or do you want me to just use 16L?
Uh, I think 16L is fine.
Okay, so then this will equal the black. Okay, so this will equal half times K times 16L is the new length and 10L is the original length. So we end up with half KX squared. This meant to be L. Yeah. That's a bit ugly. I'll just fix that. $16L. Okay. All right, and now we're just isolating for V, right? So V1, it equals, we can cancel out some stuff here. We can cancel out the half with the half. So we just divide by M and then square root it. So we have K over M and 6L squared. And then so this just ends up being 6L square root of K over M.
All right.
Okay, and this also matches in the exam, in the quiz. If you have part B and part A, it always makes sense to check to see if things are making sense. So here we got that V1 is proportional to square root of K over M times L. And in part B, we got that it's not only proportional to square root of K over M times L, but it's proportional with a proportionality constant of 6.
All right.
So that means that the dimensional analysis procedure actually worked. We got the correct formula for the dependence of V1 on K, M, and L. Now we actually calculated it using conservation of energy, and we got the same thing.
So okay, so that's good.
Okay, so now let's look at part C. Part C, it says that this is an inelastic collision now. We have a stone, the stone, so we had a stone here. There was a stone of mass M here, right? Which is, this elastic band is being used as a catapult. So we pull it back and then we release, and this stone is going to go flying.
Yeah.
Okay, so that stone, it goes flying and then it hits a piece of putty of mass capital M, which is balanced on the edge of a desk. And the stone gets embedded inside the putty. So that seems like an inelastic collision. So calculate the speed of the compound object V2 after the collision. So part C, we now have the stone goes flying. The stone of mass M goes flying and hits this block of sticky putty, which has a mass of capital M. And then we want to know what is the speed V2 of the compound object, which contains M inside it.
All right.
Do we know how to do this?
Sorry, do what exactly?
We want to calculate the speed v2 of the compound object. That's the putty plus the stone.
Right. So I guess using a momentum is a good idea.
Yeah, because if it's inelastic, then we can't use conservation of energy.
Yeah,
So,
okay.
yeah, so we'll
So
use conservation of momentum.
yeah, so initially it's just the mass, the ball,
Yeah,
and then in the final area it's the ball stuck into the putty. So it's going to be an inelastic collision where they stick. So on the left side, it would be the mass of the ball times the velocity of the ball.
okay.
And then on the right side, it'll be the mass of both the ball and the block of putty times the velocity we're trying to find.
Excellent. So we can immediately isolate and get v2 equals m v1 over m plus capital M.
Yeah.
Okay. And then we do have a formula for v1. So v1, we calculated v1 right here, right?
Okay.
So 6L square root of K over M, all divided by M plus capital M. Six ML square root of K over M plus capital M. Anything we can do to simplify this?
Maybe something to do with small mass.
Yeah, so we have M over square root of M. What's that equal to?
M over, I guess, I can't really think straight right now. I don't really know.
So we have an M and a 1 over square root of M. So we have M is equal to square root of M times square root of M.
So M times square root of M. Well, would it just be M? Or
Yeah, so if we multiply square root of M by itself, we get M, right?
yeah.
So now if I have M times 1 over root M, then I will get square root of M times square root of M over square root of M, which equals just square root of M.
So we have, would it just be 1 over M?
1 over M. Okay.
Oh,
So,
wait.
okay, I'll explain in a second. So here we had an M at the top. We had an M in the numerator. And then we also had a 1 over square root of M and also in the numerator.
All right.
So we had basically M divided by a square root of M, right?
Okay.
And M can be written as square root of M times square root of M.
M times square root of M. So so sorry, what are you asking for again?
Okay, so in this equation right here, we had an M in the numerator.
Yes.
And we also had a 1 over square root of M in the numerator.
Yeah.
So I was asking how to simplify that.
Okay, so m times square root of m is just m. So m times this 1 over the square root of m, I'm just ignoring the k at the moment. Would that be, let me think. So m times square root of m is just m.
Well, hold on. M times square root of m is more than just m. M times 1 is equal to m, but m times square root of m is more than just m.
Huh. Okay, so, well, okay, when I think about it, it would be m times square root of m would be m to the power of 1 times m to the power of 1 over 2.
Yeah.
So that means it would be m to the power of 3 over 2.
That's right. That's if you have m times square root of m. But here we have a square root of m in the denominator. So we have m times 1 over square root of m.
So that means it would be m to the power of 1 times m to the power of negative 1 half.
Yeah,
So that would be, so 1 minus 1 half would just be square root of m.
exactly. Yeah. And so that's what I was explaining here. I was saying that we have m over square root of m, right? Because we have m here, we have m, and we have square root of m. So we have m over the square root of m, right?
Yeah.
And I can write m as equal to m to the half times m to the half.
Okay.
And then I cancel out there's a root m at the top and the bottom. So then I just end up with root m.
All right.
And so that's why I put this m, and this m. That just ends up being an m in the numerator square root.
All right. That's, yeah, that's good.
All right,
All right.
so part D now. Gotta zoom in now. So it's saying, are you able to read that?
Yeah. What is the speed of the compound object when it lands on the ground if the height of the desk is h? Okay, so now we need to take into account energy.
Yeah. Now this is an elastic process because there's no more. So the inelastic part of this is over. So we have for part D, we have that this collision happened and we have now a mass m plus capital M, and it falls off of this desk. And I suppose it has V2 when it falls off the desk because the stone hit the putty and then it got stuck to it. And we calculated V2. V2 was the speed of the object after the collision. And now it's going to land on the ground.
Yeah.
This is a height of 8.
So should we do a projectile then?
Well, for conservation of energy, you don't have to worry about. So if you wanted to do kinematics, like if you wanted to know like what time it lands on the ground, then you might have to use some projectile motion formulas. But here it's just asking what's the speed at the end. So just initial energy, final energy is enough.
Okay. So initially, Well, I guess initially it will be a mix between kinetic and gravitational because it's moving.
Yeah, very good.
And then at the end, it's just kinetic.
That's right. Yeah.
All right, so at the start, it would be it'll be a half of the mass of both objects
Mhm.
Times the velocity 2 squared. Oh,
Well, I do
wait.
final minus initial, so
Oh, final minus initial. Yeah,
that's the final, and the initial is v2 squared.
yes.
Okay.
And then plus gravitational.
Yeah.
So there is no, yeah, there's no final. So the initial is just, yeah, GH.
Okay. So let's try that. So we get we can plug in. We want to isolate for v3, and we want to plug in what we got for v2, which was the 6L square root of all that stuff. Okay. So we'll get, and then we also want to put this. Okay. So so we want to put this gravitational stuff on this side, plus half m plus capital M times v2 squared, which will be 6L square root of km over m plus capital M all squared. That equals half times m plus capital M times v3 squared. Cancel this with that. And then we square this.
Yeah. Okay, so we have here. Well, it seems like everything has m plus m.
Yeah, so maybe what I did was actually stupid. I actually taught this to you last night, that when doing kinetic energy equals potential energy, everything is going to have the same mass. So we can just cancel out these things. That's actually a
Yeah.
better way of doing it. Smart. So you learned something from yesterday. That's good.
Yeah. Okay, so after that, yeah, we could multiply everything by 2 and square root, but like, yeah, not all at once though.
So
So,
2GH plus this thing now, we don't have the half. So we
so
have,
it's just everything in the brackets there.
that's
Wait.
it.
Oh
Right?
yeah, 6 squared is
36L
36. Okay.
squared times KM over this thing. And that thing has to be squared, doesn't it?
Yep. And then it's yeah, and then after that we square root.
Okay, so, and is there anything else we can do? We could factor out a 2, but that doesn't really help much.
Yeah.
So let's just do this. All right, so we have 2GH 36L squared KM over M plus capital M squared. That's right, that's the right answer. Now the last question, part E, it says, what is the limit as capital M goes to infinity?
All right.
Limit as capital M goes to infinity of V3.
Oh, as m goes to infinity, let's see here. So as m goes to infinity, then the denominator there would go to infinity. So that would approach 0 over there. So then I guess it would just be the square root of 2gh then.
Correct. That's completely right. Great. So this question, this long answer question, it looks really hard when you first look at it. Like I looked at this, I said, I've never even dealt with an elastic band with a rubber band like this before. But in the end, part A, B, C, D, E, we got through them all. This all, so you understand inelastic collisions now. So you can do conservation of momentum for the inelastic collisions, and then you're combining inelastic processes with elastic processes, and you know how to do that. You know how to do the limits. This radical simplification, it can help just to know if you have m over root m, then that's just equal to root m. If you forget how to do that, just write m as square root of m times square root of m. And probably the hardest part of this question is maybe just getting this 16L by doing the Pythagorean theorem twice and multiplying it by 2, and then so, yeah, that's a bit annoying, but it's doable.
Okay, how many questions are left?
Okay. Okay, so we've done 3 of them. There's only 2 questions left.
All right.
One of them doesn't involve collisions or conservation of momentum. It's just a block on an incline with friction. There's a question we can do right now, question 5 of this test. It has a collision. Let me get that onto the whiteboard. Okay, so 2 identical pucks of mass m and radius r are in contact and at rest on a frictionless horizontal surface.
All right.
So these are the identical pucks, 2 and 3. A third identical puck is sliding along the surface with a velocity v1i, such that it will strike the 2 stationary pucks simultaneously in a perfectly elastic 2-dimensional collision. So 2-dimensional meaning there's going to be momentum in the up and down direction and the left and right direction.
Okay.
Below the diagram to the right, it says to draw the system at the moment of contact of the 3 pucks. Add vectors representing the directions of final velocities v2, v3 of the 2 initially stationary pucks. So we can draw that right here. So it wants us to draw the 3 pucks at the moment of contact.
Hmm.
And then it says to add the vectors representing the directions of the final velocities v2 and v3.
Okay.
So for that, They didn't even do that in the solutions, but we can do that.
So,
Below diagram, add vectors representing the final velocities. So probably one of them will go somewhere and the other one will go somewhere.
and below the diagram. Okay, if it's like a perfect collision like that,
Yeah.
maybe it would be like 45-degree angles, or should I not assume such things?
Let's not assume the angle yet. Well, okay, in the next,
Yeah, it's just that if it's like a perfect collision like that,
yeah,
I don't think it would be too different from what you may
Yeah.
think.
but it says perfectly elastic, but it doesn't say perfect collision. Let's see.
Yeah,
I mean, it's
yeah.
just asking for it's just asking to draw the vectors. It's not saying to draw any angles. So in part B, it's going to say theta 1, theta 2, theta 3. We have to do that. So in part B, we'll do that. But for now, oh, for some reason, this is the same as it says part A twice. So that's just the same. So here we just first draw V2F. V2F and V3F. We draw those. Okay. So, yeah. I mean, who knows? They could also just go perfectly horizontal, right?
Right.
But they told us it's a two-dimensional collision. So all we know is that there's going to be a vertical and horizontal component for each V2 and V3.
I see.
And now it's asking what will be the directions theta 1, theta 2, and theta 3 of the velocities of the three pucks with respect to the collision, with respect to the direction of I hat unit vector after the collision. So this is where I think your intuition of it being 45 degrees might be helpful. But so the answer they're giving is actually not 45 degrees, I think. So 45 degrees is, well, 90 degrees is pi by 2. So pi equals 180, pi by 2 is 90. 45 would be pi by 4, but they're telling us it's pi by 6. They're telling us it's pi by 6. Two pucks of mass m and radius r. They're telling us that there's a radius of r for those two. So these both have a radius of r. And then there's an identical puck also with a radius of r. And what they've done in the solutions, which I still need some time to try to figure out why that is right away, but there's a diagram which is like this, and it says 2r and r and square root of 3r and theta. So we have sine of theta equals half and cos of theta equals root 3 over 2. And so the three angles ended up being theta 1 equals theta 1 equals 0, theta 2 equals plus pi by 6, and theta 3 equals minus pi by 6. So now to try to make sense of this, let me try to zoom out of it so that we can see more of what's going on. So to try to make sense of this, I think what we have is that this has a radius of r and this has a radius of r. So in total, we have 2r. And then here we have a length of r. This isn't drawn very well.
Wait, what would be the? Yeah, so okay, so I understand what you're doing here.
Yeah.
So wait, what question are we working on at the moment?
We're calculating these angles theta 1, theta 2, theta 3.
Okay, so theta. So yeah, theta 1, yeah, would be 0 because it's just gonna keep going forward, due to the perfect collision.
Mhm.
Yeah. Yeah, so that makes, yeah, all this makes sense.
So why would the angle be pi by 6 instead of, you were saying it was pi by 4, right?
Oh. Yeah, well, yeah, I think I'm wrong now because when you do take into account, well, mm, yeah, you're right. I messed up when I said pi over 4
Mhm.
because when you do take into account like the radii of everything and make that triangle there, it does turn out to be pi over 6.
Mhm. So you get all of this, you understand?
Yeah, it makes sense. It's that we basically just made a special triangle,
Mhm.
and then it's just flipped for the other particle.
So that's why it's minus pi by 6, right?
Yeah.
Mhm. And I guess this angle theta 1 could also be negative 180 degrees.
Uh, wait, what are you
If,
talking about?
so this angle is 0, but it could also be 180.
Yeah, you're right. It could also go backwards, but we do not know exactly at the moment, at least.
So we don't know whether it goes backwards or forwards.
Yeah, it doesn't say.
Yeah, and in either case, you could have conservation of momentum. So this is 0 or pi.
All right.
Okay, so that is what they gave us for the solution. Now we are asked this question. What is the ratio of the final speeds of the two initially stationary pucks, V2F and V3F? What's the ratio?
What's the ratio between? Well, if we still think about if we still think about it being like a perfect collision,
Mhm.
if we magnitude wise it's 1-to-1, and then if you actually think about it, it's like 1 to -1 kind of
Mhm.
thing,
Yeah.
because one's going in the positive y direction, one's going in the negative y direction.
Mhm. Now it says ratio of speeds, and speeds are not vectors, so we
So
don't
it's
have to
just one.
worry. Yeah, I think it's just one. Well, that's what they put anyway. We don't have to worry. If it's just a speed, then it's the magnitude. So if it was a vector, then it has both a magnitude and a direction. But because it's a speed, it's just V2F over V. Oh, sorry, it's V2F over V3F, which equals 1.
All right.
And then the final question, what will be the final speed of the initially moving puck, V1F?
Okay. Uh, what would be, okay, so for the initial, I guess we use momentum here.
Yeah, we have to, right?
Yeah, so we have the mass of the first puck times the velocity we're looking for.
Okay. So PF equals PI.
Yeah. So
So initial, or we could do PI equals PF if you want. Yeah.
yeah.
PI equals PF. Okay, and so PI is just equal to mass of the initial puck times VI, V1, because that's the V1I. That's what they gave us. V1I was the velocity of the initial puck.
All right. And then that would be equal to because the other two pucks are not moving.
Mhm.
That would be equal to the mass times velocity of the first puck final. That's what we're trying to find.
Mhm.
And then that would be plus the mass times the velocity of the second puck.
Mhm. Mass times velocity of the second puck.
And then plus mass times velocity of the third puck.
Now, don't you think we should do cos of theta, because we have this velocity vector. We're conserving linear momentum. We're conserving the momentum in the x direction.
Oh, yeah. Okay. Yeah, we're focusing on the x direction. So it would be, yeah, cos theta. And then it'll be plus m mass times the third velocity. And then that would also be cos theta.
Very good.
Yeah.
Okay, now is that enough to get what we want, which is the final speed of V1F?
No, we could continue to simplify. Yeah.
But
So
so what can we do here? We want to get V1F. And we don't know. So in the question, they didn't give us V2F or V3F. So we could just rearrange and get V1F equals MV1I minus all of this stuff divided by M. But there's something more we can do.
well, in the last part, we figured out that both the second and the third speeds are equal.
Okay.
So I think we could do something with that.
Okay. So let's maybe first cancel out all the masses.
Yeah, that as well.
And then we can use, okay, so let's make this cos 2 and cos of theta 3. That way we can actually cancel them out, right? Okay, so we're going to get V1 initial equals V1 final plus V2 F times cos theta. What was cos theta? We already calculated it to be √3/2. Now cos is an even function. So that's cos of x. So if we have positive pi/6 or negative pi/6, we get the same cosine value.
Uh, yeah. Well, well, one one is equal to the negative of the other one. But if we're talking about speed and we don't care about uh about stuff like that, then it would be the same, yes.
Actually, I don't even think one is the negative of the other because we
Oh,
have one
well,
of them going like this.
it's literally the same angle. It's just
Yeah.
different direction.
Yeah, but so the cos of this one is equal
Oh,
to
yeah.
that.
If we're focusing on the X direction, then yes, they are the same.
So it's actually twice.
Yeah, so
It's
it's
not double. It's not canceling it out. It's actually doubling.
yeah.
So we have this plus red this. So that's equal to 2 times this. So okay. So we can simplify this. Let's do cos of theta 2 equals root 3 over 2. It's root 3 over 2 plus v3f times root 3 over 2. v1I equals v1f plus 2 times v2f. So we've eliminated the v3f now due to symmetry.
Uh, so yeah, that does look good.
Okay.
And then you just isolate for the V1F.
Now, what if we want to do this without v2f in there?
Okay, so without V2F, uh, what terms should it be in though?
It should only depend on v1I.
Okay, so uh, let me think. I kind of need to go to the washroom actually. I'll be back in a few minutes. Sorry
Okay.
about that.
Yeah, we can take a short break.
Yeah.
Okay, no problem.
Hello? Can you hear me? Uh, can you hear me?
Hello?
Hi.
Okay, yeah, just 1 second. Okay, so so we want to get V1F in terms of V1I without the V2F.
Yeah.
So how can we do that? We have one equation and two unknowns.
So maybe just find another way to find another equation for V2.
Yes, very good idea.
The only problem is how to get that. Uh,
Now remember what I circled here. It's a perfectly elastic collision.
oh,
See, it says a perfectly elastic two-dimensional collision.
yeah.
So where have we used elasticity so far? We've just done conservation of momentum. We didn't use the fact that it's perfectly elastic yet.
Hmm. So, I guess if it's could you help me a bit?
Okay, well, we can use conservation of energy. We've used conservation of momentum.
Right.
We've used
Yeah.
conservation of momentum. Now we can use conservation of energy.
All right.
Okay, so how about we do that? Energy initial equals energy final.
Okay. So, yeah, final energy is equal to initial energy.
Mhm.
And is it so the initial it would just be kinetic,
Yeah.
and the final would it also just be kinetic but like with different values?
Yeah, it's all kinetic because there's no gravity, there's no spring. They haven't given us a spring constant. There's no gravity. It's all kinetic.
All right. Okay, so for the initial it would just be a half of m times the initial velocity squared. And then for the right side, it would be mass times velocity of the first final, yeah, that squared. And then the same for the other two pucks.
Mhm. Excellent. Yeah, that's exactly right. Now we can cancel this stuff out. Oh, and then we also know that the V2F and V3F are the same, right?
Yeah, 2F and 3F are the same.
2 times V2F squared. So now we have two equations and two unknowns. We have
Yes.
this one and we have this one, and we want to get V1F squared. Oh, sorry, we want to get V1F.
Yeah. So I guess, yeah, we could isolate for V2F on this bottom equation we just made,
Yeah,
and then sub it into the top, and then solve for V1F.
nice. Yeah, that's one way to do it. Yeah, okay, let's try that. But V2F, that's going to involve a square root, right?
Right.
If I isolate for V2F here, I'm going to have square root of this thing minus that thing over 2.
Right.
So instead, let me suggest here we have v1i equals v1f plus something. Here we have v1i squared equals v1f squared times something. So let's just write this one as v1i minus v1f equals 2v2f times square root of 3 over 2. And
all right.
well, hold on. We don't even need these 2's anymore, right? Because we have a 2 here and a 2 there. We have
Right.
2 and 2. So let's just get rid of that, make everything as simple as possible. So we remove, erase, erase. And then we just have square root of 3. Okay, so we have that, and then here we have v1i squared minus v1f squared equals 2 times v2f squared. Now,
Okay, so now that we did that, we then isolate for v2f on the top equation and then sub it in.
yeah, that's one thing we could do. But we know this over here is a difference of squares, right? And if I write this as a difference of squares, then I get that as one of my terms. So v1i minus v1f times v1i plus v1f.
Oh,
I have something of the form a squared minus b squared. And then this I know. This part I know from before.
all right. So, so, well, oh, so we sub in that? Huh. Uh, yeah, that's something I wouldn't think of.
Yeah, I wouldn't have thought of it either, but I'm just trying to do this. I'm trying to avoid square roots as much as possible right now, because if I isolate for v2, I'm going to have some square root. So I guess we could just say that this is equal to, because v1i minus v1f, whenever you see a difference of squares, whenever you see a squared minus b squared, you can think of doing a minus b times a plus b, right? So let's just put that in and see what happens. v2f times square root of 3, v1i plus v1f equals 2 times, oh, sorry, that's not 2 times, that's v2 f times square root of 3. And then, oh, what am I thinking? I'm doing that wrong. That's 2 times v2f squared, right? And now I have a v2f in 2 different places, so I don't have a square anymore, because I divide both sides by v2f, so I lose this v2f and I lose this square.
Right.
Okay. So I wonder if that helps. now I can actually plug in. Now I can plug in V2F here. So I will get, oh, I can't zoom out anymore. What's going on? I want to zoom out. Okay. So okay, we have V1I plus V1F equals 2 over root 3 times V2F. And V2F is equal to V1I minus V1F all over root 3. Is that what I want to do? So I'll get 2 over 6, I get 1/3. This is confusing me a little bit for a second. So I have, yeah, that seems right. 2 over 3. Yeah, everything is right. Yeah, okay. Yeah, okay. So then I have root 3 times root 3, that's just 3. So I have 2 over 3 V1I minus V1F, V1I plus V1F equals that. And then I get V1F. If I multiply everything by 3, I get 3 here, and I cancel out that 3. And then I get 3V1F plus 2V1F equals 2V1I minus 3V1I. So this means V1F equals -1 over 5 V1I. So this is the most simplified way you can write. So before we did have the right answer, but it was in terms of V2s and V3s. So now I've simplified it all the way down. Maybe I can write this a bit neater. V1I. So I've simplified this all the way down to V1F equals -1 over 5 V1I. It's just V1I times a constant.
All right.
Was there any step there that was too quick? Or anything?
Well, I guess the biggest problem I had was
You wouldn't have thought of the difference of squares yourself.
yeah.
That's the biggest problem. You just wouldn't have thought of the difference of squares.
Yeah. Wait, could you scroll back up a bit?
Yeah.
Yeah, the part where you sub in V1I minus V1F, that's what got me. Like subbing that in instead of like subbing in just one variable.
Oh, so I substituted this whole thing.
Yeah,
I substituted V2F square root of 3 over here.
Yeah, because I'm used to substituting in only one variable, not like a pair like that.
Because that's what they taught you in high school. In high school, they taught you just how to do one variable, but really V1I squared minus V1, so V1I minus V1F, you can just call that A. And then this is A equals that. So it's just one variable, it's just A, and we're just substituting A.
Yeah.
So I think that the problem there is that in high school they didn't give you experience with like complicated physics questions where you want to simplify things in terms of variables. So you've never seen that happen, but now you've seen it. I think that's a very important trick. That's a part of your toolbox. Like if you're more comfortable with that kind of thing in the future, then you're going to be ahead of all the other students.
All right.
Because what I did there, I didn't do anything wrong. You would have got the same thing if you did it your way, which was to isolate for, so you would get V2F equals V1I squared minus V1F squared divided by 2, all square rooted. Then you take that thing with the square root in it, and then you plug it in all the way over here. And then, yeah, you have a bunch of square roots. So then you're gonna have to square both sides to get rid of the square root. And then, yeah, it's just this way I avoided using the square root completely. I didn't have to have some like this is the kind of thing you end up with if you do square roots. You see this?
Yeah.
And that's hard to deal with. Like you can't simplify this easily. So I think it's good that we avoided the square root completely. But on a test, if you can't think of that, just you can do it with the square root. It just might take longer.
All right.
There's more chance of making a silly mistake.
So what's next then?
Okay, so on this exam, we've done 4 out of 5 of the long answer questions. We could do the 4th one if you want. The 5th one if you want. That is a block of mass m directed up an incline with an angle theta to the horizontal, and we're just doing some. It's chapter 1 stuff, so I don't know. Like we could do it, but there's no collisions or momentum going.
Yeah, I don't think that's important then.
Okay, so let's skip that then, and let's go on to. I'll get another exam from a different year, and we can practice some questions from there.
All right.
So, circular motion is definitely in this definitely in this chapter.
Sorry, what was your question?
So you're being tested tomorrow on circular motion. That's one of the topics.
Let me see quickly. I'll just be a second. Okay, so module 4. I don't know if circular motion is like a main part of this chapter.
Okay, you're just expected to know it from before, because on the mastering physics, we did have some circular motion stuff going on.
Yeah, I don't really know if that's going to be important, but yeah.
Okay, so we could try okay, we could try this question. This is an elastic bungee. So yeah, this sounds like it's similar to the stuff we're doing right now. So I'll get this one. So here's from a term test in fall 2004. And so we have a particle. It's connected by an ideal elastic bungee cord to a fixed vertical nail stuck in the center of a frictionless tabletop. The elastic cord has an unstretched length of 0.4 meters and a force constant, that's the K in the negative Kx, that's 650 newtons per meter. If the particle is made to travel in a horizontal circular path at a uniform rate of 2.5 revolutions per second, find the tension in the cord.
All right. Uh, sorry, let me just think. Particles. Find the tension. Okay, so for the tension, I guess we need to. I guess we need to start with F equals MA. And then using that, I guess we go to A is equal to V squared over R.
Okay.
Yeah, I kind of need a bit of help of where to start.
All right. Okay. That's perfectly fine. Let me get the marker. Okay. So ideal elastic cord stretches to a length of so the elastic cord originally was 0.4 meters, and now it stretches by a length of x. Let's say final length equals 0.400 meters plus x. That implies a force constant, F spring equals negative K X. Or, yeah, we don't really need the vector sign if it's only one dimension. Okay, so for this type of thing where they're talking about tension and stuff, it's good to think of the free body diagram of the mass. So here we have the mass, and what are all the forces acting on it?
So there's centripetal force, so there's force bringing it in to the circle.
And what's causing that centripetal force?
Oh, I guess the 2.5 revolutions per second that's moving it.
Mm-hmm. Okay, so, so what is that, gravitational force or normal force or what?
Oh, is that tension force? Yeah, that's tension force, right?
Tension force, okay. So there's tension. Okay, so we can call that tension if we want. And then there's what other forces?
Gravitational.
Okay, and anything else?
I think that's it.
There's got to be a normal force canceling out.
Yeah,
gravity.
yeah, you're right. You're right.
Okay, so these two cancel out and we end up with just tension. Now tension, how can that be written? In this case, the tension in the cord so I think the idea is to equate tension with kx, with the minus kx.
Uh,
The tension force the tension is caused by this elastic force.
yeah.
Yeah, basically we've taken it from an original length and then we've stretched it. And by stretching it, we are causing tension.
Yep.
Okay, and then, all right, good. Okay, and then this tension is causing acceleration. And that acceleration is equal to v squared over r.
All right.
Okay, so what is the net force here? What is the total, if we add up all the forces in the free body diagram, what's the net force?
The net force in the y direction it would be 0. In the x direction it would just be tension.
Yeah, and by x direction, I think you mean just inward direction, right?
Yeah, yeah.
Yeah, okay, so F net will be equal to kx, which is equal to mass times acceleration, which is equal to mass times v squared over r. Does it make sense?
Yeah.
Yeah. So what should we do next? Do you remember what they asked us for? They asked us for the tension in the cord, right?
Yeah. So I guess we solve for F net then, right?
We
Because
solve for F net, yeah,
F net is the tension.
that's right, yeah.
Okay, so we have, yeah, we have K. We have, oh, huh. I don't know where to continue.
Yeah, so yeah, so okay, well, we have that F net, which is the tension force, that's equal to mass times v squared over r. Let's see if we can get the tension that way. We have the mass, we have the r, and we have the force constant. So we have r, we have mass, and we have k, but we don't have x. If we can find x, then I think we can find the tension in the cord.
All right. So where should I start exactly?
Okay, well, so first I think we want to solve for x. So let's write that. Once we solve for x, then we can plug it into here. We're given the force constant of k. So if we find x, we can plug it into here and we get the tension.
All right, to find x, yeah, we have x equals mv squared over rk. Yeah, KR.
And then, so can we plug everything in? We have mass, we have R, we have K, and we have this 2.5 revolutions per second circular rate of the object.
All right.
So it's finishing a certain number of revolutions per second.
So we have the mass. We have is that velocity?
Well, that's frequency. That's not, you know, frequency is like revolutions per second.
Yeah.
So that is the number of times per second that it goes in a circle. That's not velocity, right? Velocity would be measured in meters per second, not in revolutions per second.
Oh.
But we can get the velocity from the frequency. So it's traveling a certain number of, so every time it does a circle, it's traveling a certain distance in a certain amount of time, right? So if it does 5 circles, how long is it going to take to do 5 circles?
Well, if it's 2.5 revolutions per second, it would take 2 seconds to do 5 circles.
To do 5 circles, I think it would take so in each second you're doing 2.5. Yeah, okay, maybe you're better at the math than me. I'm okay. How far is it going to travel? How many revolutions is it going to do in 5 seconds?
So in 5 seconds, that would be 5 times 2.5.
Yeah.
So it would be 5, 10. It would be 12.5, I think.
Yeah. So if it's traveled 12.5 circles in 5 seconds, then how much distance has it traveled in 5 seconds?
Oh, I see. So if we have it would be 12.5 times the circumference. So within 5 seconds, 12.5 revolutions. So for that, I guess we need to find the circumference
Yeah.
of the circle.
Mhm.
So that would be is it just 2 pi r?
Exactly.
Yeah, 2 pi r.
2 pi r is the amount of traveling that it does in 5. Oh, well, that's the amount of traveling it does for each circle.
And then you multiply by 12.5.
And then I multiply that by 12.5 revolutions per second. And so this is meters. Yeah, so this is, I don't have space. I'll just write this as meters. Yeah. So then that becomes meters per second, right? Well, this
Yeah.
is 2.5. I'll write this better. There's 2.5, 2 pi r revolution, meters per revolution.
All right.
So I don't need this meters here. So now in terms of unit analysis, we have revolutions at the top and bottom, and then we end up with just meters per second in the end.
Okay.
This is 2 pi r times frequency, which is the revolutions, and that's going to be in meters per second. Does that make sense?
Yeah.
Okay, so here we had, we didn't have the velocity, we had the revolutions, but now the distance you're traveling times the frequency is going to be the velocity, because here we have meters per second now, right? Because we're traveling a distance of 2 times pi times r times every time we do a circle, we're doing 2 pi r meters of travel.
Yeah.
So if I'm doing 2.5 revolutions per second, then I'm doing 2 pi r times 2.5 meters per second.
All right.
Yeah, this was per 5 seconds because I did that. Okay. So m times 2 pi r times frequency squared all over kr. So this will be m 4m pi squared r f squared all over k.
I see.
Okay. That equals 4 times the mass. Mass was 0.5 kilograms. Pi squared is just a number. Radius they gave us, that was 0.4 meters. Frequency squared, that is so 2.5 revolutions per second. So that will be 2.5 squared revolution squared per second squared. All over 650 newtons per meter.
All right.
And this is kilogram meters per second squared. So all of the unit, this is newtons at the top and newtons at the bottom. So we'll end up with exactly what we wanted, which was the position in meters. Okay, so we can plug that in. The answer is supposed to be x equals, we're solving for x here. So x is supposed to be equal to 0.09371 meters. And therefore the tension, which is equal to K times X, that is supposed to be equal to 60.9 newtons.
All right.
Okay, so this question is okay?
Yep.
Okay, so let's try to do another one. Here's a question involving both gravitational energy and kinetic energy. Okay, you can see this.
Yep.
A light rod of length L has a ball of mass M at one end. The other end is pivoted so that the rod and ball can travel in a vertical circle. Starting from the horizontal position as shown, the ball is given an initial downward velocity of v0, such that later it just barely makes it over the top of the circle. Under those conditions, what was the tension in the rod when the ball was at its lowest point? Okay. So what was the tension over here, basically?
Well, okay, so would this have to be related? Do you think this is related to energy?
For sure, because there's gravitational energy, right? There's got to
Yeah.
be some gravity involved.
So like we could say the length of the rod times 2 is like the maximum height.
Mhm. Yeah, 2 times the length is going to be the height of the. Yeah, if we make y equals 0 the bottom, if this is y equals 0, then this will be y equals 2L, right?
All right. So okay, so when it's at the center there, I guess there would be a mix between kinetic and gravitational potential energy.
Yeah, for sure.
And then at the bottom, it's just kinetic.
At the bottom, it's only kinetic. Well, yeah. Yeah, there could be gravitational energy, but if we make this, so comparative to the top, there's no kinetic.
Yeah.
Yeah, there's no gravitational energy.
Yeah.
When we do the difference between gravitational energy at the top and the bottom is where it's lowest, so we can call that 0. Energy is relative, it's just change in energy that we care about.
So let's do initial is equal to final energy.
Mhm.
And then for the initial, it would be a mass time. Wait. Yeah, it would be a mass times gravity times height. And so at that point, the height is just L.
You want to do energy initial equals energy final?
Yes.
Yeah, it's actually probably better to do change in energy equals 0, because this circle, the whole thing could be up a height h off the ground, and we don't actually know what the energy is. We don't know the absolute energy. All we know is the change in energy.
Yeah.
So if I had h, then I would have h plus 2L at the top and just h plus 0 at the bottom. And when I do the difference, the h's are going to cancel out. So I don't actually know what the total energy in momentum. I think you can write total momentum, but for energy, I think it's better to just do change in change.
All right. Yeah. So I think
So final kinetic minus initial kinetic plus
so.
final gravitational minus final.
Yeah. Okay. So final kinetic would be half of mv final squared. which is
So-
what we're trying to find.
Okay, we're trying to, what was?
Oh,
what
wait,
we're trying to find
we're
is
looking for tension. Yeah, I'm with, okay. We're going until 6, right?
Sure, yeah, we can go until 6. Yeah.
Yeah. I don't know. It's just that like going for 3 hours is a bit much, maybe.
Tiring, right? Yeah. Do you want to take a break?
Sure, actually.
We could take a break until 5, maybe. That's a 10-minute break.
Yeah, all right.
Okay. Okay, this is actually a very good question, Emma. As I'm looking at the conclusions, this is actually very interesting. I think this is a good practice.
All right. I'll see you in a few minutes then.
Okay, thanks.
Uh, I,
Hello?
hello.
Okay, you're back?
Yes.
All right, so this one's actually a very good question. So it's asking for the tension at the bottom. So what should we do if we want the tension at the bottom?
Uh, so, I don't. I'm trying to think how I could. So tension is equal to. Oh yeah, we could do the net force equation.
Yeah, okay. Okay, so F net equals tension minus gravity equals mass times acceleration.
Yeah, and then I don't really know where to go from here. Sorry.
Yeah, okay. So you want the tension. Okay, so tension equals mass times velocity over the radius. The radius is equal to L. So we have capital L plus mg. Okay, so do we have enough information to say what the tension is?
Uh, okay, so we know L, we know gravity, we know mass, but V, velocity, I guess that's the. So I guess we need to find that velocity. And so I guess we could just go back to the equation we first did
Yeah.
and then find it there.
Okay. Now, if we did that, we have the initial velocity for sure. What's the final velocity?
Yeah, that's what we're trying to find, final velocity. So we could wait. Okay, so is the velocity that mv squared over L, is the velocity here different from the final velocity?
Yeah, because it has some kinetic energy here. It's going to pick up kinetic energy as gravitational energy is converted to kinetic energy. Um, oh, can you see what I'm what I'm drawing here?
I don't think so.
Where my cursor is.
Yeah, I see where your cursor is.
So you see I'm doing a motion here.
Yes.
So it has some gravitational potential energy here and kinetic energy, and it's going to convert that gravitational energy into kinetic energy as it goes down. So it's going to speed up as it goes down because it's converting its gravitational potential energy stored up here. That's going to be converted into kinetic energy.
All right. So, yeah, I don't know how to continue.
Okay, this is how to continue. It says that the ball is given an initial downward velocity of v0 such that later it just barely makes it over the top of the circle. So the ball, it's given a v0. We don't know what v0 is, but we know that v0 is large enough that it goes around and it barely makes it around. So basically at the top, imagine if it goes all the way around and then it doesn't have enough kinetic energy to continue going in the full circle. That would mean that it gets to the top and then it's used all of its energy. Does that make sense?
Right. Yeah.
So if it had bigger than v0 as the initial velocity, then it would go around and it would still have whatever gravitational energy it has here, plus some more kinetic energy, like it would still have some kinetic energy remaining from the beginning. But it wants to say that all of this kinetic energy at the beginning is used up in getting up to the top. All of
Right.
that kinetic energy at the beginning is used in order to get to the top, so that it barely gets around.
Okay, so
So we'll do the conservation of energy for the top. Even though they're asking for the tension at the bottom, we're going to use this piece of information that it just barely makes it over the top of the circle. We're going to use that to, we're going to use the fact that it barely makes it over the top of the circle in order to do conservation of energy to get a velocity. And once we have that velocity, then we'll plug it into here.
all right, so yeah, so can you continue, please?
Okay, yeah, so let's do the delta E equals final kinetic energy minus initial kinetic energy, but final kinetic energy is at the top. We have 0. We
All
have
right.
0 minus the initial kinetic energy, which is half mv0 squared. And then what's the gravitational energy at the top?
It's just mass times gravity times 2L.
Perfect. And the gravitational energy at the beginning?
At the beginning, so the beginning is where the diagram shows.
Yeah.
So it would be a mix between two. So the gravitational at the beginning is mass times gravity times L.
mgl.
Yeah.
Okay. Yeah. So this is between beginning and top. Okay. So we have everything here. With that, we can come up with a formula for V0. So V0 now equals square root of 2GL.
All right.
I get that because the masses all cancel out. So the mass, and mass. And then this just becomes 2GL minus GL, that's just GL. And then I multiply by 2 because I have this half here. So I end up with 2GL, and I square root it to get the V0.
Okay.
Okay, so then we have V0, and now we do conservation of energy between the beginning and the bottom. Okay, between beginning and bottom. So here we have delta E equals delta K plus delta UG. The final kinetic energy, what's the final kinetic energy at the bottom?
Okay, so so the final is the bottom. So the final kinetic would be half of mv final squared. Yeah.
And the initial kinetic energy?
When you mean initial, do you mean the top or do you the beginning?
Yeah.
So it'll be mv initial squared. Yeah.
Yeah. And then the gravitational?
Okay, so final it's 0.
Yeah.
And initial it'll be mass times gravity times L.
Okay. So now we have enough to find VF, right? So VF is going to equal square root of 4GL in the end. Now I get that because I cancel out the masses. So I have negative GL, but I put that on the other side because I want VF. So I have negative GL on the other side. Then I multiply both sides by 2 because I want to get rid of this half. So I get positive 2GL equals VF squared minus V0 squared, but then V0 squared is just 2GL. So I end up with 2GL plus 2GL, that's 4GL. 4GL equals VF squared, so VF equals square root of 4GL.
All right.
Okay, or I could write this as 2 times the square root of GL. Okay, so now that we have that speed, we can figure out we know the speed at the bottom. So now we can calculate, so we want the tension at the bottom. That's going to be based on the speed at the bottom. So this equals V bottom. So then we can write down that this is going to be M times this thing squared. So that's going to be 4GL over L plus mg. So that will be now, we cancel out the L's. So we just have 4mg plus 1mg, so that's 5mg.
Yeah. So
Yeah, and that's the right answer. The right answer is 5mg.
all right.
Okay, we have time for one more.
Yeah.
Okay, so next one I'll put up here in a second. Okay, so a particle of mass m slides along a track in a vertical plane as shown. Can you see that?
Yes.
Okay, the upward curved part of the track is frictionless, so all of this is frictionless. Then we land at B, and between B and C, there's a coefficient of friction of 0.25.
Yeah.
Then we have everything to the right of C is frictionless, and we have a spring with an ideal spring constant of 500 newtons per meter. The particle is released from point A at rest, and then measured from B, where does it land?
I guess let's see. Point A, where? Okay, I see. So I guess we have to start with a gravitational to kinetic.
Yeah, that's a good idea to start.
Yeah. Should I just do it one section at a time then?
Sure, yeah. So from A to B, we have delta E equals delta K plus delta UG.
Yeah.
So the final, the change in gravitational energy.
Oh yeah, the change in gravitational. So the initial is 0. Oh wait, no, sorry. The final is 0,
Mhm.
and the initial is it's mass times gravity times L/2. Yeah,
Yeah, okay. All right, so we want to isolate for what?
we would like to isolate for velocity b.
Yeah, okay. So that one, again, that's root 2 GL for the same reason as before. We
Yeah,
cancel out the masses. We multiply by 2. So we get VB squared equals 2 GL. Well, 2 GL over 2, so it's just GL. So we get VB squared equals 2 GL, and then we square root both sides. So that's the velocity at point B. Now it travels from B to C along a surface with coefficient of friction 0.25.
okay. And then I guess after that we need to do from B to C.
Okay.
And so this time we have to find how much slower it gets due to friction. And then for that, I guess we need to do an F net equation.
Okay.
So we have F is equal to MA, and then that would be equal to well, maybe not F net though.
Yeah, not F net, because we have a certain kinetic energy here. We want to know the kinetic energy there. The friction does work, so you can just use the work kinetic energy theory.
Yeah, yeah, right. Okay, so the work kinetic energy theorem is I think it's like delta K is equal to the work of friction.
Yeah, exactly.
And so delta K, so delta K itself is equal to the final kinetic minus the initial kinetic energy.
Okay.
Yeah. And then the work of friction is equal to mu K times the normal force times displacement.
Okay, so it's equal to this thing times displacement and the magnitude of that vector product.
Yeah.
Okay, and then we know that if we want to calculate the absolute value of a dot product, we can do the absolute value of the individual vectors times the cosine of the angle between them. And that is equal to, in this case, we have what you said, which was Fk times the normal force times distance times cos theta. And this is equal to mu k mg, right?
Yeah.
And what about d? What's the distance we're traveling? They gave it to us here. So that's the distance we're traveling, right?
The distance is the displacement is L.
Yeah. So the distance is just L. And I suppose we don't even need these two anymore. And then the cosine of the angle between them?
I guess it would be 90.
The
What?
friction is going this way and traveling is going that way.
Oh, sorry, I was thinking about friction to normal force. Yeah, so it's 0.
It's not
Oh
zero.
wait, no,
So,
180.
yeah,
Sorry.
yeah. So that's very important because you said normal force, but we've got to remember in work kinetic energy theorem, our work is the force multiplied by the displacement in the direction. Well, we have a vector product. We have the force vector and the displacement vector. The force vector is going to the left. The displacement vector is going to the right. The normal force isn't doing work in this case. It's the friction that's doing the work. The normal force is doing work against gravity. So we could do the work due to normal force, but it's not moving in the normal force direction. So we would just have that the work due to normal force is equal to the work due to gravity. So
Right.
those cancel out. Okay, so this work formula, it's important to remember how it works. We have work equals delta K. Work is force dot producted with displacement. And that means if our friction is going to the left, friction force is going to the left, displacement force is going to the right, we have cos of 180 degrees. So that's negative, right? Mu K mg L cos of 180, which is -1. And this all equals half m VC squared plus, minus half mvb squared.
All right.
All right, so then we have masses cancel out. That's nice. We can multiply everything by 2 to get rid of these. So then what do we get? We have VC squared equals, so V equals the square root of a bunch of stuff. We're going to have VB squared plus 2 mu K GL.
Yeah. So I don't think we could simplify C any further. Can we?
Well, we have VB, I think, right? VB is equal to square root of G.
Oh, yeah, you're right.
Okay, so we can put that in.
And then the square would cancel it out, and then it'll just be GL plus the rest. Yeah, and then we could also factor out GL, yeah. And then it'll be 1 plus 2 mkg. Oh yeah, not G.
Yeah, because we factored out the G.
Yeah, yeah.
Okay, all right, so that's good. We have BC. And now it's actually going to travel. So it travels from B to C. And then from C, it's going to travel. So the flat section to the right of C is frictionless. So it asks where measured from B does the particle eventually come to rest? So where does the particle come to rest? It comes down like this. It hits that spring. It probably goes like that, bounces back, and then comes back to somewhere here.
Yeah.
And we're looking for this distance, capital D.
Yeah.
So any idea where it's going to land?
Well, it's probably going to land. It's going to land after it bounces back between B and C. So it'll be like it would be from 0 to L from point B. Yeah.
0 to L.
Yeah, if you count it says where measured from point B, so B is equal to 0.
Yeah.
So the position it would stop at would be like from 0 to L.
It will be somewhere between 0 and L.
Yeah.
Yeah, yeah. Okay, so that's true. Yeah, it comes to rest somewhere between B and C, so somewhere between 0 and L. So where's it going to come to rest?
Well, I guess we need to keep calculating then.
Yep.
So now, wait, we have the velocity. Didn't we calculate the velocity of C?
Yeah, we calculated the velocity at C.
So at this point we could we need to work through the spring force.
Yeah.
And then see how much speed it has when it exits the spring going the
Now we
other way.
could do that, but we could take a shortcut and we can just ignore the spring entirely.
Really?
Because the spring force is a conservative force. You've learned about conservative forces?
Could you explain them quickly? I
So
might
basically,
know.
whatever energy is going to be lost going into the spring, it's going to be gained back on the way out.
Right.
Because that force is just half kx squared. And whatever k, so whatever x, your velocity, so you're going to lose kinetic energy in order to create spring energy. But then that spring energy, the same spring energy that you just created from velocity is going to be used in order to give you more velocity again. So it's reused.
All right, I see.
Because this is an ideal spring and it's a frictionless, after to the right of C, it's frictionless. To the right of C, it's frictionless. So we don't lose any energy here. We lose kinetic energy, it gets converted into spring, but then the spring energy, that gets converted back to kinetic. So because there's no friction, because it's ideal, there's no loss of energy, we have conservation of energy. Whatever happens in that spring comes back. Whatever's lost to the spring comes back.
All right. Yeah. And it says it's friction. Yeah. Okay, so we could just assume the speed is the same going the other way.
Yeah. So so it landed at C, it had kinetic energy, it lost some of that kinetic energy, converted it into spring energy, then that spring energy got converted back to kinetic energy. And so now we have half mvc squared kinetic energy over here. And we're going to lose some of it due to work by friction. And we're going to lose that kinetic energy until it completely stops. And we want to know where it stops.
Yeah, so what we do is we do what we did before.
Mm-hmm.
But this time the initial speed is speed C we calculated, and then the final speed is 0.
Okay, so we do work due to friction equals delta K. So that's going to be final speed is 0, initial speed is, well, initial kinetic energy is half m, and then this thing, GL times 1 plus 2 mu K. Okay, and that's work due to friction. We have what here? What's the work due to friction
here? The work due to friction is, what we did up there.
Minus mu K mg x, because we don't know how far it's going to go. Minus mu K mg x, or we can call it, I think I called it capital D here. Okay, yeah, we can call it x, and then D is going to be equal to L minus X. Okay. So let's do X. Okay. All right, so we solve for X.
Yeah.
We have mg and mg. So we get X equals, we multiply everything by 2 as well, right? Let's get rid of that. We put a 2 there. So we'll have 2 mu kx equals, we can cancel out the negative as well. So now we have L times 1 plus 2 mu k. Yeah.
Yeah. And then after that, I guess we just divide. Yeah.
Mhm.
All right.
Right.
So okay, so it's 5:30 right now. Oh wait. Oh yeah, we're not done yet. Because X is so so what we got here at the sorry, the X we got here, is that like it's not what we're looking for, right? It's X is the distance from the spring to the stopping point, but we need from point B to the stopping point.
Exactly. Yeah.
Yeah, so we, I guess that would mean it would be L minus what we got to
Yeah.
get the other.
Yeah. So we'd have D equals L minus X, which equals L minus all this stuff, which is just going to be L over 2 mu k.
Yeah.
Yeah.
All right. So yeah, I think we're good now.
For this question, yeah.
Yeah.
Okay, so still 5:30, right? 5:30.
Yeah.
So I can show you another question if you want.
I guess we could continue.
We could do one more maybe. Let's see. Okay. You have another question from the same exam.
Okay.
Oh yeah, actually, just quickly, this mu k is 0.250.
Yeah,
So that's 1/4.
yeah.
Okay, so if you do 1/4 here, you'll get,
Oh, we could have an actual number.
yeah. So, and this number is actually pretty cool because we're going to have L/2 times 1/4. Yeah,
Yeah,
what's that
and
equal to?
yeah, it would be, it would be 2/4, so it would be, yeah, it would be 2L.
So 2L. What that means is that basically it travels the distance L and then it comes back and it stops exactly at B.
Oh,
That's where it stops. So it goes from here, it goes all the way there, and then it comes all the way back. So that's the distance of 2L. L and L equals 2L. So the point where it lands is exactly point B. That's only because the mu k was equal to exactly 1/4. If mu k was equal to something else, then it would land, if mu k was greater, then it would stop before B. And if mu k was smaller, it would keep going up to A. But because mu k was equal to exactly 1/4, and this height was exactly L/2, it ends up that this mass just goes here, and then it comes back exactly at B.
all right.
Okay, so here, this is the last question, I think. So Professor Brandon's first grandson, Matthew James, was too young to go trick-or-treating on his first Halloween this year. So his sister, Caitlin Elizabeth, and his cousin, Sydney Jean, decided to suspend MJ in his jolly jumper from the ceiling of their front porch where he could watch them trick-or-treat around the neighborhood. The jolly jumper acted like an ideal spring with an unstretched length of 1.2 meters and with a spring constant of 98 newtons per meter. So we have the jolly jumper acted as an ideal spring. So the unstretched length is 1.2 meters. And the spring constant K equals 98.0 newtons per meter. The girls attached MJ, of total mass 10 kilograms, in his costume to the lower end of the jolly jumper and released him from rest. So now there is a 10-kilogram mass at the bottom of the spring. If the ceiling to floor distance was 3.7 meters, okay, so from here to here is a height where height equals 3.7 meters. How close to the floor did MJ come after the girls released him? So the girls release him. How far away from the floor does, so let's call this X. The boy lands a certain distance from the floor, right? So here we have kinetic energy, sorry, yeah, we're gonna have kinetic energy, but we also have gravitational energy and spring energy.
All right, so okay, so the cross. Okay, so yeah, just start. I guess we need to do something to do with energy, right?
Of course, yeah, because there's going to be gravitational and spring energy being converted to well, there's going to be gravitational energy being converted to spring energy and kinetic energy.
Yeah. So I guess for initial, or we could, yeah, the other way. So we have both forces for gravitational, kinetic, and spring.
Mhm.
So we have so we have those three forces.
Yeah.
So we have delta E is equal to 0, which is equal to delta K plus delta U, which is gravitational, and also delta U for spring. Yeah.
Yeah.
And then, okay, so for delta K, and wait, the top, could you scroll up to the actual question for a second? I just got to see where the actual starting point is. Is it? Okay, so he is released. So he's released from the top minus the length of the spring.
Mhm.
So if it says ceiling to the floor distance was 3.7, so I guess we could say the initial height is 3.7 minus 1.2.
Initial height. Yeah, that's right. Yeah, the initial height will be 3.7 minus 1.2. Yeah.
Yeah. Okay, so let's
call that L for now, because if we start plugging numbers in the beginning, then we're going to have square root of 4.26 times 1.91 newtons divided by, like, it's harder to simplify. You know how we simplified the square root of m in that case? We had m.
Yeah, you're right. You're right. Okay, so for delta K, we have K final minus K initial. K final is half of mv squared.
Well, K final should be 0, because we want to know the height at which the baby lands. So the baby will fall down, and then it says if the ceiling to floor, how close to the floor does MJ come? So MJ is going to fall to a certain distance, and if he still has a distance at the bottom, then he's still moving. I mean, if he still has a velocity at the bottom, then he's still moving, so he hasn't stopped. So how far does he travel until the kinetic energy becomes 0?
Oh, so wait, so there's initial kinetic energy, even though it's at a
well, no, there's not initial kinetic energy, but so yeah,
so
it
is
starts at rest and he ends at rest.
oh, so there is no kinetic energy in this case.
There's kinetic energy, but
Like,
kinetic energy produced due to the gravity, but that kinetic energy is then converted into spring energy, and it's lost.
like there's no kinetic energy we need to calculate.
Yeah, because there's 0 at the bottom and 0 at the top. It's all converted to spring.
Okay, so
You could even have skipped the kinetic energy and said kinetic energy is a conservative force. So ignore kinetic energy, and you
yeah.
delta E with gravity and spring.
All right.
You understand conservative forces? They taught you that?
Yeah, it's just that I didn't think about
Using it.
like when I thought, oh, yeah, you're right. I
So
just didn't,
friction is not a conservative force. You learned that, right?
yeah,
But spring energy, gravity, gravitational energy, and kinetic energy, those are all conservative. So when you have conservative forces, you can use conservation of energy. And when you have non-conservative forces like friction, you have to use work kinetic energy theory.
all right. So let's just go, yeah, to gravitational. So the initial would be L, so mass times gravity times L.
Yeah,
And then the final would be mass times gravity times X.
that's right. Yeah. So do you want to use L and X? Okay, we can do that. So,
Yeah. Yeah, you suggested we shouldn't sub in any numbers just yet to make it easier.
yeah, that's right. And then, well, okay, sorry, I should have said MGL minus MGX. So then we could just call this MGD. So let's call this difference between X and L, let's call that D. Then we have just MGD.
All right.
Okay. So that's gravity, and then we have spring, right?
Yeah, and so for spring, spring energy, it's half of mx of kx squared, right?
Mm-hmm. And well, X, we called X this. So,
Like okay, x as in like spring displacement.
and how much is that?
So for final, it would be it would be it would be the height of the building minus how much minus L or D plus X.
So the spring,
Oh wait.
it
Yeah,
starts
you're right.
here.
No. Okay. Even better. It's H minus 1.2.
The
Or
final. So the final is when the thing lands on the ground.
yeah, when it lands at that point.
So how much has it traveled?
Well, it would be D.
Exactly. That's right. Yeah, because it's going from equilibrium to X. That means it's traveling D.
Yeah. And then the initial 0 then.
Yeah. And then minus 0, because at the beginning it's in equilibrium.
Yeah.
Okay, that's good. All right, we can simplify this then, right? We have, this is all gone. We have just MGD plus half KD squared. I think I did do something wrong. This is MGX minus MGL. So that's the wrong way around. This should be MGX minus L. So that was actually negative D.
I see.
I had this, yeah, so negative. So then we can solve for D, which is the distance. So let's remove that and remove that by dividing everything by D and multiply everything by 2. So then we have 2mg equals kd. And so 2mg over k equals d. So if we do this in the calculator, we should end up with d equals 2 meters. And then because this entire height, h, equals 3.7 meters, then the distance above the ground is going to be wait, this is going to be I don't know why I said 2 meters. I meant to say 2. Yeah, okay, so this is 2.0 meters. 2.00 meters. Max distance from the ceiling is 1.2 plus 2 equals 3.2.
Wait, how do we figure out D's two? Oh yeah, we just
2 times
solved
mass
that.
times g over k.
Yeah, and then if we know D and H, we could find X pretty easily.
Yeah, I seem to have the wrong answer. It looks like d plus 1.2. .7. Okay, yeah. So basically h equals 1.2 meters plus d plus x. So plus 2.00 meters. This is 1.20 meters plus x. So then x equals 3.7 meters, 3.70, I guess, minus 1.20 meters, minus 2.00 meters. And this just
Yeah.
ends up being 0.50 meters.
All right.
Perfect.
So I guess we are done now.
Yeah, so we practiced quite a lot of, let's see how many. We did 1, 2, 3, 4, 5, 6. We did 6 questions today in just 3 hours. And these tests are usually 2 hours, and they have like
2 questions.
2 long answer questions and then some multiple choice.
Yes.
So I think that puts you in a good position. We just did 6 questions together in
All right.
2 hours plus breaks.
Yeah.
That's a lot of talking and stuff, right?
So where do you save all of this work?
Okay, so I'm gonna save this right now. I'm gonna do export this board to PDF. To export your thing, you need to create at least 1 frame. Each frame will be a separate page in the okay, create frame. I don't know how to do this. Create frame. Okay. Custom. Okay, I'll just make the whole thing a frame. bigger. This is a new software I'm using because Zoom didn't allow me to show the question at the same time as the whiteboard. So I had to rewrite all the questions for you on Zoom, which was a bit annoying. Oh, what's going on now? Undo. Okay. I want to make this frame bigger. But that's moving stuff. Okay, undo. Okay, so this frame. Oh, nice. Okay, so. Oops. Frame. Okay. Okay, looks like that's going to contain everything. Okay, so that's my frame, and then I will do export to PDF. Export. Okay, so you can zoom into this. Oh no, the quality is crap.
That's not good.
Yeah, you can't even read it now, right?
No.
Okay, so okay, so that's how this software is free, but then they this is my first time using the software, but basically what they've done is when I do the save the PDF, it says small file size and best quality, but I can't click on best quality. I probably have to upgrade to a new version.
Yeah, that's not good.
Yeah, because this software was so much better than Zoom, and while I was using it, I was like, "Oh, this is cool! I can scroll, I can paste new images here and everything." But then, then right when you want the save thing, it asks for the premium version. So, what I could do, we could take screenshots of it from here. That's going to be perfect quality, right?
Hmm.
Also, what I have is the YouTube video for this. So I'll post the thing to YouTube right after this, and then you'll have it all in there because that's the screen. That's the same resolution as what the screen share is showing.
All right.
Okay, so for now I'll do that, and then I'll try to figure out some way to work out how to save these whiteboards better.
All right. Yeah, I guess I will see you soon.
Okay, excellent. Okay, see you soon.
Goodbye.
Okay, goodbye.